last lesson in this semester. Kind of crazy to think about. Is optimization. Okay, so our final application of derivatives. Now, optimization is trying to minimize or maximize something. Finding the most something will happen or finding the least something will happen. So we often hear terms like finding the least time, the greatest profit, shortest distance, maximum volume, minimum waste. Those are optimization problems because you're trying to optimize something, whether it be in a minimal form or a maximum form. We're going to look, basically I've just got examples for you, is what we're going to look at. Okay, I'm going to try and get you some of the basics. These can range from easier problems to incredibly difficult problems. Okay, so my goal is to try and get us mastering some of the basics here. Okay, that's, basics here. So, example 1. Find two positive numbers such that the sum of the first and twice the second is 64, and whose product is a maximum. Now, one of the things we're doing, it kind of reminds me of related rates problems, and that we have to write a couple of equations. We have to look for relationships and write those equations. So, as you look at this one, the beginning of that forms a pretty obvious equation, if you ask me. You see an equation you can write? Two positive numbers, that's the sum of the first and twice the second is 64. Officially, if I want to be official here, what do you want to use for the first number? I'm shortcutting. Let x equal the first number. And if that's the case, then I'm going to say let y equal the second number. So write me an equation that we can use as part of this problem. Sum of the first and twice the second is 64. So what's that equation? Yes? No? You guys are quiet. I'm hoping that's because you're writing it down on your own. X plus 2y equals 64. Now, the other piece of information we know, whose product is a maximum. What do we mean product? Product being xy, right? And I'm just going to put this down at the bottom because I want to work with this previous equation a little bit. But that's the other piece of information we know, is that the product is a maximum. You usually have two equations here. We're trying to maximize this product, yes? So this is the equation we're going to work with, we're going to do derivatives with. However, we don't want it in terms of two variables. So kind of like related rates, you're sometimes trying to get it down to one variable. And that's what we're going to do here, is we want to get it down to one variable. This x plus 2y equals 64 is one of the, it's probably our secondary equation here, that if we solve this for one of the variables, we can then plug it into the other equation. I tend to work with x's more than y's, although technically we could go either way with this problem. I'm going to solve this. I think we could go either way. Now that I think about it, why would we go? Interesting. Okay. I'm going to solve this for y. And if I solve this for y, that means what? 2y is 64 minus x, and so y is 64 minus x all over 2. You can change it, you can reduce it some there, or we'll reduce it later. Now, if we look at the idea that this is what we're trying to optimize here, we're trying to maximize it, I'm going to write it as f of x, and for the moment, I'm going to say is x times y. Except we really don't want x and y in there since it's f of x. What do we want to do? Take what your y equals and replace it. So instead I'm going to write this as f of x equals x times 64 minus x all over 2. In order to maximize or minimize something, you know we're going to be talking derivatives, right? I mean, hello, we're in an application of derivative chapter. I would not take the derivative here. We can clean that up and make that better. Okay. First of all, I can multiply that x in. If I multiply that x in, 64x minus x squared all over 2. If I clean this up and split it into 2 terms, again, I'm trying to think of what's going to be easiest to take the derivative of. 64x divided by 2 is 32x minus, I can say x squared over 2, or I can say 1/2 x squared. It doesn't matter what you write there. If you prefer x squared over 2, that's fine. That's going to be your easiest form to find the derivative of, isn't it? So, let's do it. We find the derivative. What is the derivative of f of x? Derivative of 32x is 32 minus the derivative of 1/2 x squared is x. Okay. How do we find our maxes and mins? Take your derivative, set equal to 0. So if I set 32 minus x equals 0, we're going to find that x is 32. Now, one thing I want to caution you of. I feel like, I almost want to say 99% of the time, maybe 95% of the time. I feel like more often than not, you find this answer, this is your answer. However, could they throw a trick in there? They could. And so one thing you want to be in the habit of doing is kind of checking to make sure we're trying to maximize, right? We're trying to find a maximum. How do we check and make sure this truly is a maximum? And this is where we could use a sign chart. Okay, and this is kind of just I'm double checking to make sure it is a max. Sometimes we'll have multiple critical points, so we have to go to the sign chart. We don't have an option. But here, I only got one answer. So unless I did something fully wrong or this is like a trick question, this is probably the max. But let's double check. So this is a first derivative sign chart. Plug a number smaller than 32 in. Well, if I plug a number smaller than 32 in, and I'm looking right here, you could look right here, but nope, wait. Let's look at the derivative, huh? Okay, we look at the derivative. 32 minus any number smaller than it is going to be a positive. We plug in a number bigger than 32. 32 minus a number bigger than it is going to be a negative. Does that verify it's a max? Yes, because my sign of my derivative changed from positive to negative, which does indeed verify it is a max. Okay? That type of justification, it doesn't say to justify here or anything, but, and it's not even so much as showing the sign chart, because the sign chart is not necessarily official justification, but if you had to write in the statement that 32 is a max because the derivative changes from positive to negative. Okay? So we can agree that 32 is one of the two numbers that will maximize. How do I find the other number? If x is 32, can we plug it in there? Right? That's probably the easiest way to find y. So y is 64 minus 32 over 2, which is 16. Because my problem asked me to find two positive numbers such that the sum was such and the product was such. And so 32 is one of those two positive numbers. But if you recall, it was x and y to find this maximum. And so we found x. The connection between x and y is that equation there. Okay? So I'm just going to write here that my numbers are 32 and 16. I do not have any justification written down for this one. I didn't ask for it. I don't know that it necessarily asked for it a lot. So I'm thinking, man, we got almost half an hour left. Try again. Okay. Questions on example 1. Okay. Shall we look at example 2? A rancher plans to fence a rectangular pasture adjacent to a river. The pasture must contain 180,000 square meters in order to provide enough grass for the herd. What dimensions would require the least amount of fencing if no fencing is needed along the river? Okay. So, one thing I'm going to do here is I'm going to draw a picture. Laugh at me all you want, but I'm going to draw a picture. Okay? It's a rectangular pasture, and what's the key though? One side is along the river. So my rectangular pasture, one side is along the river. The river side needs no fencing. I guess the cows aren't going to swim away. Now, the pasture must contain 180,000 square meters. What is 180,000 square meters? That is area. Okay? What dimensions, so we're looking for a length and a width here, would require the least amount of fencing if no fencing is needed along the river? Okay, trying to get it all together. So I'm trying to think if we've done problems like these before or not, or if I'm just thinking back to calculus previously. Let's see. I know my area has to be 180,000 square meters. Just me gathering my information. I need to pick dimensions. Okay? We know we're going to have one side here and the two sides the same. I don't see a reason that it matters. I'll be honest, when I checked mine against the answer key, I labeled mine fully opposite, and it all works out in the end. So, you guys care which way we go here? I mean, I know I labeled mine, I said X and Y. I know hers were reversed. She had one long X and two short Ys. So, doesn't matter. Okay, what kind of equations are we going to need here? Because think we usually have two equations. One of them we're going to try to maximize, minimize. The other is our connection between variables. Okay, so one of the things we're talking about here is that area is x times y, and we already know that x times y is going to be 180,000, right? So that's part of the information I need to write down. What else do we need to know? What are we trying to, it said the least, so we're trying to minimize. What are we trying to minimize? The the amount of fencing, what is that? We're not trying to minimize or maximize area. Perimeter, yes. So what is the perimeter of fencing here that we're going to need? Okay. The way I have it written here is 2x plus y. I did leave a gap there because I'm getting ready to do something. Sorry. Now, so 2 important equations here. I saw an area connection. I saw a perimeter connection. I was told what my area is, wasn't I? So, and we're trying to least amount, we're trying to minimize, trying to find the minimum amount of fencing, which means my derivatives are going to have to happen on my perimeter. I'm going to get down to one variable, though. I have this equation here that has 2 variables in it, doesn't it? Solve this for x or y and plug it into the other one. No, we don't want to, because we don't know that the perimeter is 0. We'll have to take the derivative before we set equal to 0. Okay? So on mine, I generally tend to solve for y. And so y is 180,000 divided by x. I'm not saying you'd have to, though. And so the idea now is that I can take this 180,000x and I can plug it in for y. And then I will have a perimeter equation that I can call p of x, if you will, or I can call p, and that is what we will be working with. Because it will be my perimeter equation, 2x plus y, except instead of y, I'm going to say 180,000 over x. In order to minimize or maximize, take the derivative. Now, before I take the derivative, I don't know if you guys need me to, I'm going to rewrite this and say it's 2x plus 180,000 times x to the negative first. Maybe you need that visual, maybe you don't need that visual. To each their own, right? You've seen how many steps she skips, so not encouraging, but okay. Now we're going to take the derivative. I'll do derivative of 2x for you. That's 2. You guys can do the next derivative. What's the derivative of 180,000 x to the negative first? Okay. I was going to say negative 180,000 x to the negative second. Miles went ahead and wrote the next part, right? Perfectly fine. Again, and those are steps that I am perfectly fine with you guys skipping if you can handle that. Some of you are saying yes, please. Some of you are saying no, thank you. So, okay. Now, with that in mind, derivative, and we've got our derivative. Now we're ready to set it equal to 0. In this situation, once I set it equal to 0, I would put, since there's a fraction with an x in the denominator, I would put pieces on opposite sides. So like if I keep the 2 here and I add over the 180,000 over x squared, because then my brain thinks cross products. Because it's like 2 over 1, right? So my brain thinks cross products and says 2x squared equals 180,000. So half of 180,000 is 90,000. So x squared is 90,000. When we take the square root of 90,000.
Well, no.
Okay, so let's address that. Officially, we should say plus or minus 300. However, take into the consideration of what we're doing, and we really only need to say 300. And I'm guessing if you look at her answer key, you probably don't even see the plus or minus there. This is one where you can kind of skip over the plus or minus in your head. Don't forget about it though, right? Now, what is this? This is my 300, technically be 300 meters. This is my width, right? Assuming, is it truly the least amount of fencing? Is it truly a minimum? So should I do a quick check? I probably should do a quick check. Now, on something like this, should you ever plug in a negative number? No. Just something smaller than 100, or 300, excuse me. If I plug in something smaller than 300, 2 minus, I don't know. This is where I would grab the calc there. I'm pretty sure it works out to be negative here, right? Officially, 0 would be that endpoint. When you plug in something bigger than 300, say 400, that ends up working out to be positive. Okay? With that in mind, decreasing, increasing, that verifies that, yes, this is a minimum. The sign doesn't need change from negative to positive. Okay? So, what are my dimensions? Use one of these, right? Either use this guy or that guy. If x is 300, then y is 600. And so my dimensions are 300 meters by 600 meters. And I guess we're stopping there. That's 2 solid examples. We haven't talked about one where we need to do endpoints, so tomorrow we'll plan to do at least a couple more examples. As I said, I'm not 100% sold. I'm going to do all the examples because there are some rough stuff in this at the end of this. We'll see how timing goes. There's always a chance we'll go back and look at a few of the others that we skipped over that you guys think might be helpful. We'll see. Okay. Friday, I'm not here, so that will be a work day. I should hopefully have a review worksheet. It can be a catch-up day, whatever it needs to be. A calculus day.